All right, everyone, it is 7:30, so let's get started. I'll go ahead and start sharing my screen right away. Let's jump over the tutorials. And we're going to start with tutorial 4, which is the k-nearest neighbors. Supervised learning is a buzzword in the machine learning field, and it refers to problems in which you're trying to predict a label from a set of features. And really there are two types of supervised learning problems there, and they're differentiated by the types of labels that you're trying to predict. So a regression problem is one in which the label can take a numeric value over a continuous range of values. And classification is the situation where the label can take only a finite set of values, a discrete set of values. So linear regression, which we talked about yesterday, is an example of a regression supervised learning technique. So it's a little bit confusing that we use both the term regression in this general sense of trying to predict a continuous label and specifically to linear regression. And then we can confuse it even more because there's logistic regression, which is essentially a classification technique. So it gets a little muddied, but a regression problem in the general sense is a problem in which you are trying to predict a continuous label from a set of features. So previously we've discussed linear regression, and today we're going to talk about k-nearest neighbors, which is a simple machine learning algorithm that can be useful for both regression and classification. Today we're going to be focused on it as a classifier. In the future we may explore it also as a regression technique. And in particular, we're going to set up a simple financial classification problem, and we'll also use it as a jumping off point for starting to talk about various issues like holdout sets, cross-validation, variance, and the variance bias trade-off, etc. So we can crack into it. Let's start by loading up the package that we're going to need. So we're going to import pandas as PD, import numpy as NP, import seaborn as SNS, import sklearn, and we're going to also import matplotlib.pyplot as PLT. So let's talk a little bit about the data that we're going to be analyzing. The VIX is a volatility index published by the CBOE, and it's a general measure of 30-day implied volatility for the S&P 500 index. And what that means is it takes in option price data from options which are about 30 days to expiration, and then calculates an implied volatility measure based on those. So using that same methodology, the CBO publishes a variety of other volatility measures on other stocks and other ETFs, such as the Russell 2000, EWZ. And most of these volatility measures also have a 30-day tenor. That's the standard tenor for most volatility indices. But there are several CBO indices that have different tenors, i.e. they're based off of options with maturities that are different from 30 days. And in particular, for the S&P 500, there are indices for 9-day, 3-month, 6-month, and 1-year volatility. And so in this tutorial, we are going to use these various volatility metrics with different tenors. We can now go ahead and read in the data that we are going to be analyzing. So this VIX data, VIX equals PD dot read CSV, VIX KNN CSV. I don't know why I did it. So the next line just removes this first row that has some nans in it, but you can just say DF VIX drop NA, and then DF VIX head. So there's our data, and what we have for each day is a change in these various implied volatility indexes, as well as the S&P 500 return for that day. And I'm not including the 1-year index because the data on that was just incomplete. It didn't go back very far. So before we start jumping into classification properly, let's do some simple visualizations to get a sense for our data. And in particular, I want to introduce the Seaborn pair plot function, which is really convenient for simultaneously visualizing various pairwise relationships for columns in a data frame. So here's what that looks like. SNS.pairplot dfvix vix 009 vix 030 vix 090 and vix 180. Just calling out the columns that I want to take a look at. And there we go. Pretty cool. So what we have here on the diagonal are histograms of these various columns. And then we have these pairwise scatter plots. So this is the VIX 9-day, I'm sorry, the VIX 30-day on the x-axis and the VIX 9-day on the y-axis. So on and so forth. Here's just a little question for you guys to ponder. And I've decided, since you guys are such a quiet group, I won't try to force you guys to answer, but you're free to if you want to. I'll just let you take a couple minutes and ponder this question. How would you characterize the pairwise relationship between the various VIX indices? Okay, so very simply, all these various indices are very positively correlated with another. You can see that. And we'll see that in various ways. We'll see that in a PCA analysis that we're going to do later. So yeah, and one thing that I'll save that comment for later. So here's a very simple classification problem that we're going to set up. As we discussed last time, the leverage effect is a stylized fact about equity index volatility. And basically it encapsulates the relationship that when returns are negative, implied vols tend to increase. When returns are positive, implied vol tends to decrease. And we quantified this relation previously with a linear regression. And we found the relationship to be quite strong, a solid R squared for a finance context. Based on the knowledge of this relationship, let's consider it a simple classification exercise, which is to define whether a return was a gain or loss based on various changes in the various VIX indices. So in the language of machine learning, our label is going to be today's return as a gain or a loss, and our features are going to be changes in the VIX indices, in the various VIX indices. And let me say, when I first set up this problem, I felt like it was a little bit of a silly toy problem, but I actually learned about this hedge fund called Normalize, where they basically outsource their predictive analytics to anyone who wants to sort of participate in a Kaggle-like competition. And they get paid in cryptocurrency. It's a pretty weird setup. But the interesting thing is, so a couple interesting things. One is that they anonymize all their data. So that way people don't know what they're actually trying to predict, so that all the assets are anonymized. And the predictions that they make are not returns predictions, but simply gain or a loss. So it is sort of this binary classification. Obviously, they do so with a much greater set of features, and it's a trickier problem, but they do reduce the predictive analytics in an asset management context down to a simple gain or loss prediction. Before we get into actual k-nearest neighbors classification, let's talk about some really simple rules-based classifiers or other classifiers that will help us determine some bounds for performance, determine whether k-nearest neighbors is working particularly well or not. So one thing you could do is you could randomly guess, right? And that really represents the lower bound of performance of any learning model. So we should really have if you recall, accuracy is the standard measure that we use in a lot of classification contexts. And that just measures the percentage of your predictions that were correct. In this type of situation, we would expect a 50% success rate because we're just simply randomly guessing between two possible outcomes. Oh yeah, and I should also add, if you have a success rate of significantly less than 50%, well then you still have information there. There's still predictions going on. Just do the opposite of what your prediction suggests. So we're going to do some random number generation. Therefore, we're going to go ahead and set our random seed. So we always get the same outcome. Random seed. Set it to, 100. And we'll use that to make our random predictions. df_vix rand label, new column in our data frame, np random rand int 0 to df_vix shape. So let's look at df_vix. Okay, now we have a random label with which to compare to our SPI returns. And let's figure out our conditions. So condition 1 is, df_vix rand label equals 0 and df_vix by return less than or equal to 0. And condition 2 is df_vix rand label equals 1 and df_vix SPI return is greater than 0. I don't know why I have both less than or equal to and greater than or equal to, because there's overlap there. And then we can just check the number of rows. We can use data frame masking to check the number of rows if we filter by these two conditions and compare that to the number of rows in the entire data frame. df_vix condition 1, condition 2, shape 0, and then we'll just divide that by df_vix shape 0. And we see it's very close to 50%. Okay, so that's random guessing. Another thing we could do is we could just always predict a gain. So this is a great example of a classifier with a high bias and a low variance. So it's highly biased in the sense that you're going to be wrong on, anyway, we'll get into bias and variance later, so I apologize. So it's actually smarter than random guessing, even though it's very, very simple, because we do have some knowledge that over the long stretches of time, equity markets tend to rise. And also rarely are there jumps up. So the typical pattern is, slow, steady gains, and then the occasional drop, and little drops along the way. But in general, there should be days of more gain than there are loss. So let's see what happens. So if we always guess that, then we can see the number of times we're right as simply the percentage of days which were gains. So here we used masking to find the days that had positive returns. Okay, so about 55% of days there were gains for SPY. So our always guess gain would have been right 50% of the time. Okay, we could also do a leverage effect rule, right? We could say, we know that there's this implied leverage effect, so we could just look at what happened in the volatility markets And if there was an increase in volatility, then we would guess that there were negative returns, and if there's a decrease in volatility, we'd predict a gain. So let's calculate that out. So that's based on two conditions. DF VIX 0, 3, 0, and we'll just use 30-day VIX. If VIX is greater than or equal to 0, and DF VIX SPY return is less than or equal to 0, and condition 2 is DF VIX 030 less than or equal to 0, and DF VIX SPY return greater than 0. I'll just do this. Okay. So let's see, that runs perfect. DF VIX mask on condition 1 or condition 2. Check the shape. DF VIX shape 0. And it looks like the leverage effect is, this leverage effect rule is actually very accurate and is right about 80% of the time. If we use k-nearest neighbors along with these VIX indices to make predictions about gains or losses, we should really be doing quite a bit better than 80%, or else we're really not adding much value other than just capturing the leverage effect. And spoiler alert, our accuracy doesn't really improve that much. It does improve a little bit, but basically all we're capturing is the leverage effect. And now we can finally get to k-nearest neighbors itself. So k-nearest neighbors is a simple classification algorithm based on a very intuitive principle. The idea is that feature observations that are similar should have similar associated labels. And in that case, feature similarity is determined by distance in Euclidean space. So here's how it works. Let's say we're trying to predict a label for some given feature observation, and we have some training data. What we do is we find the k feature samples in the training set that are closest to our feature observation. We find the labels associated with those k closest samples. And then the k-nearest neighbors prediction is simply the label that occurs most often in that set of k labels. So if you check 10 of the closest points and 6 of them are a gain and 4 of them are a loss, then your prediction would be gain. And k-nearest neighbors is an example of an instance-based classifier, is a name that's associated with it. But really all that means is that there's no fitting process, right, other than storing the training data. And the prediction algorithm really amounts to just calculating distances between the feature observations and the feature observation in question and the features in the training set, and then sorting by those distance and grabbing the ones that are closest. So we'll need to do just a little bit of data wrangling to get our data in order. So let's do that now. So the first thing we're going to do is define a simple function that's going to add a column to our data set where L stands for a loss that day and G stands for a gain. We can do that now. DF labeler. It's going to take in a return. If return less than 0, return L, else return G. Now we can use this labeler function along with the apply method, which is going to effectively vectorize this function and give us a new column, which will be what we want. So currently in there, we still have this random label that we produced above. We can go ahead and get rid of that. Drop rand label axis equals 1, in place equals true. Well, let me run this multiple times or will you get mad at me? Oh yeah. Now let's go ahead and add our label as a column. We'll call it SPY label 0 equals dfvix SPY return apply labeler dfvix head. So now we have our gain loss label, which is what we wanted. Our first iteration of k-nearest neighbors is going to be predicting VIX with a single volatility index, or rather changes in a single volatility index, and we'll use the standard 30-day VIX for this. Moreover, we're going to use the entirety of our data set for training the model. In future sections in this tutorial, we will have holdout sets and do cross-validation and things like that. We'll begin by importing the constructor function for k-nearest neighbors. It's in the sklearn neighbors module, k-neighbors classifier. And again, as is great about scikit-learn, it really always just follows the same steps for fitting a model. We're going to do feature selection, identifying the training data, the features that we want to use. We're going to instantiate a model using the constructor and set the model hyperparameters. And we're going to use the .fit to instantiate our model. Hyperparameters are not I don't think we've introduced this concept yet. But hyperparameters are various parameters that have an impact on how your model does its fitting. And once we get into tree-based methods, there's lots of different hyperparameters. The main one for k-nearest neighbors is the number of neighbors, the size of the neighborhood that you're going to use to average over or survey. However, there are some other ones. I don't really mess around with them. We can take a look once we've done this. So let's go ahead and get started. First, we'll do our feature selection. Big X is dfvix, and we're just going to use the VIX 30-day. Y is dfvix SPY label 0. Those are our labels. Next, we'll do our model selection, by which I mean we'll just instantiate our model with the constructor function. And if we do a shift tab, we can see if there's other, there are other things they do. Weights, probably, I don't know what algorithm does. Metric is what determines the distance, the type of metric used to determine the distance between points. So yeah, there are a variety of them. I've never really messed around with them other than K, or yes, K, i.e. the number of neighbors. I'm guessing in our situation, it would have minimal impact. Have I run this? I have not. Oh, we need to fit the model, sorry. I got distracted. So we'll fit our model, CLF, fit, XY. So now our model is fit, which really is nothing more than, there's no real fitting going on anyway. So in a classification setting, the typical score that we give is the model accuracy, which is simply the percentage of your predictions that were correct. And we'll see in our student loan tutorials and assignments how accuracy can break down as a metric, but in this situation, it works just fine. And as a refresher for linear regression, the score function gave the R squared. So let's check our score, CLF, score, XY. So a very small gain in accuracy between this and the simple rule-based leverage effect. So really what we're just capturing is leverage effect. No big deal. We're really just using this as a way of trying to understand k-nearest neighbors, and also k-nearest neighbors is useful for understanding some other concepts around machine learning. But we are better than random guessing. So that's, now let's try predicting with multiple features, which in our case means multiple VIX indices. And really what we'd like to see is, does our in-sample accuracy improve as we add additional features? One thing to note is that when you have multiple features, it's important to normalize the features, which means make them mean 0 and standard deviation 1. So that, and the reason for that is that so none of the features sort of dominate. But we can talk about that a little more during the discussion question. And as scikit-learn often does, there's a convenient function called scale, which has the behavior that we want of subtracting away the mean and dividing everything by the standard deviation. So let's import the scale function from sklearn, pre-processing, import scale. Next, we'll do our feature selection. X equals df vix, vix 009, vix 030, vix 090, vix 180. And we'll grab our label, which is df vix spy label 0. We'll say values to just grab the values. No. Now we'll scale our features with the scale function. We'll call it XS, and then we'll just say scale X. We can do our model selection, i.e. just instantiate our model with the constructor function. And then we can fit our model, CLF, fit, and we'll print our score. Print CLF, score, X, Y. And I'm sure I made a typo somewhere. There we go. Okay, very slight improvement, but we did improve by adding these additional features, which is good. So here's a question for you to think about. What would happen if we added option volume to our analysis, but we didn't normalize the feature set? Okay, so kind of a simple answer, but if you think about it, option volume is something that has an order of magnitude in the hundreds of thousands, tens of thousands, millions. And these changes in VIX, as we have them, are much smaller numbers. So if we're calculating Euclidean distances between vectors of points like this, and then one of the components of the vectors is a number that's multiple orders of magnitude bigger than it, then the option volume is simply going to dominate the analysis. So that's a heavy-handed example that shows why you need to scale your features. All right, so here's your code challenge, and it's to rerun the multi-VIX index analysis, but set K equal to 1 and then take a look at the accuracy. All right, so let me kind of do this along with you guys. So we just need to rerun all of this code, but change number of neighbors to 1. Let me run that. And we see we have 100% accuracy, which looks amazing, right? But as we'll see, this is a little bit of a mirage. And the way it's kind of easy to see, because since we're just measuring our accuracy in our with our in-sample accuracy on the full training data set, basically what we're doing is anytime we take a feature observation in our training data, the one point that's closest to it in the training data is itself, and therefore you're always going to be correct because you're just matching the label outcome from that point itself. So, and as you'll see later, the k nearest neighbor is equal to 1 has has a much lower out of sample accuracy than if you have a larger number of neighbors. And so that's a classic example of overfitting the data. It looks amazing in sample, but really you've just overfit your data. And then when you put it out in the wild, the performance really suffers. Okay, let's talk about holdout sets. So far, we've been only looking at our accuracy score in sample, meaning we're taking the full training data set and then we're calculating our accuracy on that. And this gives really a skewed perception. It gives a skewed perception of how accurate the model is going to be on data in the wild. So one thing that we can do to try to account for this or try to mitigate this is to divide our data into two subsets. One for training the model and fitting the model, and then another one for testing the model. And the model selection module contains a convenience function that helps us do exactly that. And the function is called train test split. So let's go ahead and import that now. From sklearn, model selection, import train test split. And let's go ahead. So we'll do our feature selection, df vix, vix 009, vix 030, vix 090, vix 180. Then y equals df vix spy label 0. We're going to scale our features. We're going to say xs equals scale x. And now we're going to use our train test split. So this is a canonical way to use it, we're going to say X train, X test, Y train, Y test. And the reason that works like that, and you can just do that, I think this is a little bit of inside baseball here, but so if you just do, let's say 1, 2, 3, 4, that actually produces oh, I see. Oh, I could do it like this. It actually produces an array. It's just one of these little shorthands that Python allows. Oh, it's a tuple, sorry. That's what they call them. A tuple is a little bit like a list, except it's immutable. So anyway, that describes this notation a little bit. Train, test, split, XS, Y. We're going to say that our test size, we're going to grab 20% of the data, and that's going to be our test data, and then 80% of our data is going to be our training data. So we say test size is equal to 20%, and we're going to set our random state equal to 0. Now we'll instantiate our model, CLF equals K nearest neighbors classifier, N neighbors equals 10, and CLF dot fit X train, Y train. There we go. Now let's look at our accuracies. Train is print CLF score. Oh, CLF dot score. X train, Y train. So that's our in-sample accuracy from our fitting or training. Now our out-of-sample accuracy test is print CLF score X train, X test, Y test. So we have slightly lower accuracy on our test set than our training set. And that's actually always going to be the case. Often the times the disparity can be quite a bit greater. But we have a very simple toy problem that we're working on. So your coding challenge is to copy and paste the above code and rerun it using K equals 1 and see if the spread between the training accuracy and the testing accuracy is larger or smaller than when K equals 10. Okay, so let me do this with you guys and talk about it a little bit. So that is all looking the same, except we want to change our number of neighbors to 10. And then let's take a look at our training data, our training accuracy, and our testing accuracy. Oh, I can't do this. Okay, there we go. So here we see our training accuracy is 100%, and then our test accuracy is 80%. So the disparity is quite a bit bigger than in the situation where K was equal to 10. And again, that's sort of a way of demonstrating overfitting. It's the classic situation is which you have a very high in-sample accuracy, but then out of sample, it's much lower. And that's a good indication that you've overfit the data. And when there's a less of a disparity, then the model is essentially performing better, even though the training accuracy might look not as good. Any questions? Okay, so in the previous section, we used train test split to partition our data so we could check the accuracy of our model on the observations that were not used in the fitting process. So, and when we did this, we noticed the accuracy of the model is lower on the testing set than on the training set. And the testing accuracy is going to be more reflective of how the model would perform in the wild. But this raises a question, why should we stop at doing the splitting just once? We could do a train test split multiple times, and each time we hold out a different part of the data for our testing data, and then we train it on the other part. And then we'd have a variety of different testing accuracies. And this collection of accuracies in aggregate is going to form a more robust measure of model performance. And we're going to do this quite a bit in our student loan tutorials. And it's going to be a little less trivial in those situations. So, but this multiple train test split idea is exactly what the notion of model cross-validation is. And good old scikit-learn has something, a function called cross-val score that does exactly this. And so we can do this in a very small amount of code. So let's import cross-val score from sklearn model selection import cross-val score x equals, let's call this feature selection. I won't have us type this anymore. So those are our features, the 4 different VIX indices. Our label is going to be df VIX SPY label values. Let's scale our features. XS, we will scale X. Then we're going to instantiate our model. CLF K neighbors. And then we'll do our cross-validation. Cross-val score CLF XS Y cross-val. Number CV equals 5. So that means that we're going to do a 5-fold cross-validation. So we're going to split our data up into 5 parts, each of equal size, 20%, 20%, 20%, et cetera. And in each iteration of the cross-validation, we're going to save 20% of it for testing and then train with the rest of it and then calculate an out-of-sample accuracy with the testing set. And it does this all in one foul swoop. So there we go. Here are our various out-of-sample accuracies. And again, let me underscore, sklearn is awesome because implementing something like this would have just been about writing a bunch of boilerplate code, and instead, in a couple of lines, you've got exactly what you want. And all you have to do is stick in your model, your features, and your labels. And this could be any model. It could be a decision tree, random forest, gradient boosted trees, all kinds of fancy things. All right. This is a big chunk of code. We've been talking about the variance bias trade-off, and we'll talk about it a little bit more during the slides that we cover today. But this gives us a nice visualization of it. And again, as we saw above, when k equals 1, the in-sample accuracy is perfect, but the out-of-sample accuracy is relatively poor. And in this situation, it's sort of this synthetic fact, right? But there are other situations in a more general setting where you have good in-sample accuracy. You can see that a lot with decision trees, where you super overfit the data, and then when you go to apply it out of sample, it looks terrible. So another way of thinking about this is when k equals 1, we're allowing for maximum model complexity. Or said in another way, we're attributing a ton of information to every single value in the training data set, but all the data is inherently noisy, but we're sort of attributing a lot of importance to all that noise. So here's one way to visualize this, and I'm just going to uncomment this code and we can talk our way through it. Okay, so this is the usual thing that we do. We're doing grabbing our features, scaling them. We're going to do a train test split, and then we're going to let our number of neighbors range from 1 to 20, and we're going to fit it and then calculate our accuracy scores for our training set and our testing set, and then we're going to plot those. So that's what we've done here. So to read this, when k equals 1, we know that the accuracy, the training accuracy is 100%, but the testing accuracy was much lower at 80%. And at 5, we can see the training accuracy is, let's call it 87, while the testing accuracy is, call it 83. So that's how to interpret this graph. And effectively what we're doing is we're reducing the complexity of our model or our algorithm. And I don't mean complexity in the computation sense. I mean complexity of the machine learning algorithm. We're making our model more coarse. There's more sort of averaging going on if we increase the value of k. And in that situation, the training accuracy and the testing accuracy converge. So here's a little question for you guys to ponder, and that is, based on this graph, which value of k would you choose and why? So I can give you the way I think about these problems and the way I think they're generally thought of. So we want, let's call it the highest amount of model complexity that doesn't overfit the data. I think that's a good general rule of thumb. And here we're sort of signifying overfitting the data by a large gap between training data and testing data. So if I look at this, I would say, you know, there's this point where they perfectly converge, but that's just kind of a noisy point. I would say somewhere in the 6, 7 range, maybe even 10, that I would set my my k equal to around there, because I feel like past that you aren't getting much more convergence between the two, and eventually the more and more the higher K gets, the more sort of coarse your model gets. So we can also use, so above we use train test split effectively as a way for thinking about what we want the value of K, which is our hyperparameter, to be. And yeah, all these numbers were based on a single holdout set, a single test set, and a single training set. But we could also do this with something similar with cross-validation, and we would have a more robust measure. So in a cross-validation setting, you're going to end up with 5 or 10 and if it's an n-fold cross-validation, you're going to produce n different test set errors. And what you can do is you can just average those, for example, and have a single measure of test error. That's what this code does. Let me just uncomment it. So again, we just grab our features and our labels, we scale them. We're going to let our number of neighbors range from 1 to 50. And then we are going to have these CV scores, which is just the mean of 10-fold cross-validation. So for each one of these values, we're going to run a 10-fold cross-validation that's going to produce 10 different testing accuracies. And then we're going to just take the average of those testing accuracies. For whatever reason, they like to use misclassification, which is simply 1 minus your accuracy to visualize this. And I don't know why, maybe like this L shape, because there's an L shape up here, so all the graphs are sort of consistent. But here we can see that as K decreases, we start to have increasing misclassifications. The average of those 10-fold test scores gets higher and higher. Or the accuracy gets lower and lower, the misclassification gets higher and higher. And then we can see things kind of chill out a little bit here and plateau. Discussion question for you guys to think about for a couple minutes is, based on this graph, which value of K would you choose? We want as much model complexity as we can get without having a high misclassification error. And right, I would say things kind of level out here. So maybe based on this graph, I would say in the sort of 15-ish range. I'd keep it in the sort of between 10 and 15. So it gives a slightly different answer than we might get up here. But all right, let's move on to some slides. So as you well know by now, this course is about performing analysis on financial data, and this data is generated in a variety of ways in finance. Trading activities, you have company regulatory filings if you want to do something like quantitative investing using accounting measures. Debt servicing activity, if you're investing in portfolios of loans, you'll want information from the entities that are servicing that debt to get a sense for who's defaulting, who's not defaulting, who's prepaying, et cetera, et cetera. The task of actually collecting all this data, processing it, storing it, getting it into a usable format is really a massive undertaking. And there's an old joke in data analysis that really 90% of your time is just cleaning and wrangling the data. And unfortunately, that is a true statement, and it might even be underestimating how much time gets spent. Depending on how you look at it, fortunately or unfortunately, we're not going to have time to address that component of data analysis because we simply just don't have enough time, right? All your time would be spent cleaning a bunch of messy data. So we're going to be performing data mostly on clean data sets. I do make a point in my tutorials to at least have some data processing things. If I've cleaned the data and then I still need to process some of the data, at least a little bit, I try to keep those steps within the tutorial to give you at least a sense of data wrangling. So when you're performing analysis on data, there's really two different objectives that you might have. One is making predictions or forecasts about unknown things in the world. In finance, that's typically future events. Is this stock going up? Is this stock going down? Is this pool of loans going to pay off early or not? And there's also inference, where you're trying to learn more about the process, the worldly process that generates that data. Our course is going to be focused on prediction, but sometimes it's going to be useful to take more of an inferential perspective to actually improve those predictions. The old machine learning versus statistics question. This is a question I've asked myself a lot. I've talked to a lot of different professionals about, and ultimately I've decided I'm going to leave the strict demarcation between these two to the philosophers and the academics. But from my perspective, they're both fields of study that deal with extracting insights from data. There's a significant overlap between the concepts, the terminology, the underlying mathematics, like probability theory, linear algebra, and real analysis. It seems pretty clear to me, though, that in machine learning, there's a much greater focus on prediction, whereas in statistics, there's a much greater focus on inference. And so given that in this class, we're going to be focused more on prediction, we're going to tend to be more sympathetic to the machine learning point of view. And we'll also use machine learning terminology and notation, even though there's probably analogous ways that you could state it in more classical statistics terminology. So to that end, let's actually talk a little bit about the various terminology, just because you'll find that people tend to be pretty loose about how they use these terms, and they'll use them interchangeably, and sometimes it's easy to get confused. So in general, we could say that we take a set of inputs to predict a set of outputs. That's how you might say it in plain English, if you will. In statistics, you'd say you have a predictor and a model that will take in the predictor and give responses. In more classical, let's say, statistics, or in a probably econometrics course, you've probably heard about independent variables that are fit and then give you a dependent variable. So you fit a model to independent variables and it produces the dependent variable. And in pattern recognition or machine learning, which is the language that we're going to tend to use the most, we talk about features and learning a model to predict a label. So we're going to be learning labels from features, predicting labels from features. But again, these terms get used interchangeably, so get comfortable with all of them. So we've already talked about this a little bit, but when we seek to predict a quantitative label, this is called a regression problem. And when we seek to predict a qualitative label, it's called a classification problem. And certain prediction methods are better suited for regression or classification, and other ones work just equally well for both, like k-nearest neighbors, decision trees. You can use them for both classification and regression. Okay, let's talk a little bit about typical notation. And these are mostly the conventions that are used in Introduction to Statistical Learning and Elements of Statistical Learning. So often when you speak of machine learning in the abstract, you really use the language of math to discuss it. So we're going to set up some notation. Starting point for any analysis is typically a training set of data. And from that training data, we derive our prediction mechanism. A training sample consists of observations of features as well as their associated labels. So each feature observation is going to have with it a label associated with it, an outcome associated with it. And typically the number of observations in our sample is going to be denoted by a lowercase n. We're going to denote the number of features, the dimension of features, to be p. And sometimes it will be useful to put all our feature observations into an n by p matrix. So there's n rows, the number of each, and so effectively each row is a one feature observation for the p features. So the ijth coordinate is the ith observation of the jth feature, the first observation of the pth feature, the first observation of the second feature. So if we need to refer to it, xi is going to refer to the ith row of x. So it's the p vector that's the ith feature observation of all the features taken at once. Sometimes we're going to have to refer to the columns of the features, which is all of the observations of a given feature. And so that's going to be denoted with a bold xj. And another thing you could do is you could express this matrix as these column vectors lined up, like a vector of column vectors. Sometimes that's useful. And then the n feature, the n labels associated with our n feature observations is just going to be boldface y, which is going to be a column vector or an n by 1 matrix. Let's talk a little bit about random variables. As we mentioned above, the starting point for our data analysis is always some kind of sample data set. And it will be useful to think of that data as being the realization or the outcome of some random process or random variable. And since we have p features, we are going to think of this as being a multivariate random variable. And we're just going to denote the whole thing as capital X. We'll also think of the y, the label as being a random variable. And if it's a numeric random variable in a regression problem, we'll denote it capital Y. And if it's a classification problem, i.e. a discrete outcome, we're going to denote it as G. I don't know why G, maybe category, like the G in category. Okay, so just at a high level, let's, vectors of length n, number of observations, are lowercase bold letters. Scalars or vectors of length p are going to be lowercase normal font letters. Matrices are capital bolds. And random variables are capital normal fonts. Statistical learning. So statistical learning is one way to think about machine learning. We're going to talk about a few different lenses through which to think about machine learning problems. So let's say we have some quantitative label y and p features, which we believe are going to be predictive of y. And our assumption is that there's some functional relationship between x and y. So y equals f of x plus, I don't think this is epsilon, I don't forget it. I'm just going to call this epsilon because I don't remember what it is. And we have that epsilon is some random error that's independent of x and has a mean of 0, okay? So in this way, we can think of f as representing the systematic information that x provides about y. And statistical learning refers to the various approaches for estimating f. And the estimation of f is going to be denoted by f hat to distinguish it from the actual relationship f, which is often unknown. It's a theoretical fiction, or it's just a theoretical unknown. So let's say we have a set of observations of observed trading data that consists both of inputs and outputs, features, labels. And our goal is to apply statistical learning methods to our trading data to estimate this F hat. So at a high level, what we do is the observed inputs right here are fed into some kind of learning algorithm, which usually takes the form of a computer program. The learning algorithm produces an output F hat of X, which is associated with each observed output. Typically, the learning algorithm is some kind of iterative process that's going to effectively modify F in response to changes in the error terms, right? The actual outcome versus the estimated outcome. And once we've completed this iterative process, the hope is that the artificial outputs, the predicted outputs and the real outputs are close enough so that F hat is a good predictor of all the inputs that might be encountered in practice. So that's at a high level what we're trying to do here. There are two broad categories of statistical learning methods to keep in mind. One is called parametric methods, where we're making strong assumptions about the functional form of F. Linear regression is a great example. We assume that functional form is a linear function. So these methods are going to be inherently more restrictive, but also more interpretable. So linear regression is a great example. It's very easy to describe how you take an input and then calculate the output from it. So, and that's very easy to convey from one human to another. Non-parametric methods, and k-nearest neighbor is one of those, it makes no explicit assumption about the functional form of F. So they're very flexible. They can be very flexible, but they're often very hard to interpret. That's one of the issues with things like decision trees, random forests, or even worse. It's kind of a black box, and it's hard to describe to someone, okay, if I stick in this output, here's why. I'm sorry, if I stick in this input, here's why I get this output. Model interpretability often is an expense of model flexibility. So when inference is important, interpretability is important. But in predictions, and increasingly I find that in machine learning, all you really care about is the predictions, and they're somewhat sympathetic to this idea that you don't need strong model interpretability as long as you're creating good predictions. And I actually find that to be a bit of a clarifying point of view, to be honest. And one reason why I found statistics to be a little bit distasteful, but probably taken to an extreme, and I think there are these people, there's plenty of data scientists out there who don't really have a sense for the context in which they're practicing, and therefore they're a little out of control, or they're just not particularly effective. And part of that can come from thinking that all you need to do is have accurate predictions, even if you don't really understand the underlying business use cases or business dynamics that create the data. So another way we can think about machine learning is function approximation. So in the function approximation paradigm, the observed training observation are viewed as points in P+1 Euclidean space. So P is the number of features, and then +1 for the label. And F is some function that has domain equal to the input space and has the following relationship with the data. And it's useful to find the goal is to find a useful approximation of F. And the function approximation paradigm typically uses a lot of Euclidean geometry and probabilistic inference. So least squares and maximum likelihood are two tactics for function approximation that we're going to use. We've already used least squares. Okay, let's talk about, now going to talk about linear regression and k-nearest neighbors regression. And these, it's an interesting, and I'm still trying to wrap my brain around this, but many machine learning algorithms are either some variant of either one of these or some combination of these two. And so really you can think about them as the foundation of a lot of more complex machine learning algorithms. So we've got a situation in linear regression where we have an input x with a constant and then p different features and a numerical output y. And linear regression approximates the relationship between x and y as this linear function. And if we stick x and y together in x and y hat together, it's a linear subspace of that has dimension. No, it's a linear subspace of Rp plus 2. And notice that the function x transpose beta is linear, and that if you differentiate that beta is the points in the steepest uphill direction. So how is it that we go about choosing this beta hat? For any generic beta, we could define the residual sum of squares as summing up the errors between the prediction and what actually happened. You square it, you sum it up. And what the beta hat that we want is the one that actually minimizes this residual sum of squares. So since this is a quadratic function, there's always a minimum, although it's not necessarily unique. And we could use matrix notation to rewrite the residual sum of squares like this to make the minimization problem a little bit more obvious. So if we differentiate with respect to beta, we get the normal equations. And if xtx is non-singular, then there is a unique solution to the normal equations, which is given by this. And I don't want to make, I'm kind of just going through these pretty quickly. These sorts of details are not going to be a big part of the course. I'm much more interested in writing code and implementation, but I wanted to give you guys a little bit of background on this. So for a given feature observation x naught, the predicted label is x naught transpose multiplied by beta hat, which is given by this. So that's one of the pillars, right? Linear regression. Now let's talk about nearest neighbors regression. So let's say we have a set of training data right here. And for a given feature observation X that may or may not be in the data, the training data set, the nearest neighbors predictor is this. So what you do is you take the K training features that are closest to X. That's what NKX is. For all of the points in NKX, we see what the the label is. And again, the label is numeric in this situation. And then we just take an average of those. And again, for good measure, it's worth saying that nearness is determined here by the standard Euclidean metric. But you can use other metrics, and even scikit-learn allows for generality in that respect. So that's pretty simple and intuitive, and it's worth noting that a large subset of popular machine learning algorithms are really just variants of linear regression or k-nearest neighbors. Okay, let's talk about classification a little bit. So again, we've got our training data, and we want to estimate F, the relationship between our features and our labels. And in this situation, our labels are going to be categorical. They're going to have a finite number of outcomes. So if F hat is our estimate, then we're going to define the training error rate, the accuracy, as simply the average of, this gives you the percentage of your predictions which were correct. This is another way of denoting that with the indicator function. Let's talk a little bit about the Bayes classifier, which is, in some sense, a theoretical ideal about the best you can do with a Bayes classifier. So test data, as we've already talked about, is observations that are not in the training set that were used to train your model. For a set of test observations, the test error is defined as yes, I guess it should be 1 minus this average, or I does not equal I for a non-equals versus equals. But in any case, so it's actually possible to prove that the test error is actually minimized when you choose whatever category actually, right, it's minimized when you choose a category that maximizes the conditional probability. So again, for we have a feature observation X naught, and if the algorithm to determine a prediction, if the prediction mechanism is simply giving you the category which maximizes the conditional probability of Y given X, that's actually the best. It's called the Bayes classifier, and it's really the best you can do. This is the optimal error rate given by the Bayes classifier. So in a sense, the Bayes classifier represents the best you can do. And of course, the issue is we don't really know in practice what this conditional probability distribution is. So by definition of the Bayes classifier, for X equals X naught, we're going to have this as the error rate. And then the overall error rate is simply going to be 1 minus the expected value of this. But again, we can't use the Bayes classifier directly because we don't know what the conditional probabilities of X given Y. But it's in some sense this unattainable gold standard. And one thing that you can do is if you have simulated data and some other classifier. So in situations where you have simulated data and you know what the underlying probability distributions are, you can compare your classification or the classification algorithm in question to the Bayes classifier, because then you actually do know the probability distribution. So let's talk about the nearest neighbors classifier. So many classification methods actually seek to estimate y given x and classify according to maximizing that conditional probability. So k-nearest neighbors is one where we're really modeling this conditional probability as the probability of a given the probability of a given category or a given one of the discrete outcomes of that the label can take in that neighborhood, the K neighborhood. Okay, statistical decision theory. This is another lens through which to look at machine learning. And actually, I think it's a cool one. All right, statistical decision theory, another paradigm or lens through which to think about machine learning. Okay, let's say we have x, which is some real valued feature vector. So it's a random variable, p-dimensional random variable, and y is some real valued label. And that we have a joint distribution between the two given by this right here. That's the joint distribution of x and y. So we're seeking an f of x, an f that takes in x and predicts y. And in order to develop this statistical decision theory, we'll need a notion of a loss function, which is basically some way of penalizing prediction error. And the most common loss function is this, where you simply take the difference between the actual label and the predicted label, and you square it. So under the squared error loss function that we have above, the expected prediction error is given by this integral. And then we can use conditional expectation. We can break this down in terms of the conditional expectation of y given x, and we have this identity. So the expected error of f is the conditional expectation of y minus fx squared, and then the expectation of that. So if we want to minimize the expected prediction error, we can do that in a pointwise fashion. And the pointwise fashion simply says that the resulting f that minimizes this expected square error is the conditional expectation of y given x, which is referred to generically as a regression function. Yet another use of the word regression. So really what we've said here is that in this statistical decision theoretic framework, that the conditional expectation, this function right here, is really the optimal estimate because it minimizes the expected prediction error. And if we were to use a different loss function, above the loss function that we used is referred to as L2 norm. If we use the L1 norm, which is just the absolute value of the difference between y and fx, then we would get a slightly different optimal solution, which is the conditional median of y for x equals x. given that x equals x. But median and mean are both measures of location, so these two results are very similar. Now let's think about how to view nearest neighbors under this paradigm. So nearest neighbors is an algorithm that really tries to apply this recipe of conditional expectation, this regression function, pretty directly. And specifically, at each point in the input space, call it x, we ask for the value f hat of x to be the average of all the y. So all the labels with xi equals to x, we want their average. But there's typically at most one such value if you have a large enough set of features and a small enough data set. It's almost always the case that there's only one at most one feature observation in your training data that is equal to x. So rather than do a conditional expectation on xi equals x, we do we average over all the y's where xi is in a k neighborhood of x. So there's really two different approximations that are occurring here, approximations to the regression equation. First of all, expectation is approximated by simply averaging. And two, conditioning on a point, rather than conditioning on a point as we are doing here, we are conditioning on a region close to that point. So under mild conditions, which we don't even need to worry about, if both n and k approach infinity, such that n is growing faster than k, which is given by this identity here, we can see that the nearest neighbors regression converges to the optimal condition. So basically, our f of x is going to converge to this conditional expectation. But so at a high level, that kind of gives you the sense that if you have a large enough data set, you are going to converge with k nearest neighbors to the optimal solution. However, so that sounds great, and it sounds like maybe that means that the nearest neighbors is all we need, and we just need a large enough amount of data. And that is in some sense true, but it's usually almost always the case that we don't have large data sets. This convergence actually occurs very, very slowly, especially if there's a large number of features. And this issue is referred to as the curse of dimensionality. So if you think about it, if you have a large number of features, then your data set is going to be becoming more and more sparse within that space. And so that's why the more features you add, the worse a k nearest neighbors regression is going to work. But it is true that if you had an extremely large data set, k nearest neighbors would give you a nearly optimal solution. You couldn't do any better than k nearest neighbors. Okay, let's see how linear regression fits into this decision theoretic framework. So in linear regression, we assume this simple linear functional form. And we could then directly see that the expected error loss is simply the expectation of y minus x transpose b squared. And I wrote some notes to myself here, so I apologize. I do need to understand this better. But after differentiating, we can see that beta is equal to this identity here. So intuitively, we're not really conditioning on x, rather that we're just using our assumption that there's a linear functional relationship to pool over the values of x. So least squares really amounts to replacing conditional expectations by averages over the training data. Again, we're just sort of averaging over training data. So least squares versus nearest neighbors. How do we think about these two? So both k-nearest neighbors and linear regression are approximations to this conditional expectations with averages, but they have very different assumptions. So least squares assumes that f of x is globally linear, whereas k-nearest neighbors assumes that f of x is locally constant. So within small neighborhoods of the input space, the function is basically constant. But I think the key insight I garnered from this material was that really what you're doing in any kind of machine learning algorithm is you are taking conditional expectations over your training data. So in some sense, you're just doing really fancy averaging to come up with your estimates, which makes sort of intuitive sense. If you have a set of numbers and you had to give your best guess of what a number is, oftentimes the mean is simply your best guess. So let's talk about how we could put a classification problem in this decision theoretic framework. So if we're trying to predict a categorical label G from a feature X, then we'd arrive at the following optimal estimate. The best estimate is the category which maximizes this conditional probability. So in nearest neighbors, we're seeking to estimate this conditional probability directly. Okay, let's talk a little bit about bias and variance. The variance bias trade-off is kind of a big concept in machine learning, and oftentimes in an interview setting, you might be asked to describe the variance bias trade-off. So let's say we're in a situation where we're trying to forecast a quantitative label from a set of features. Y is going to be our label, X is going to be our features. And there's, of course, an assumption of some kind of functional relationship between F and X with some noise term. And let's say F hat is our estimate, our prediction estimate for F. If we calculate the average squared prediction error of our estimate, we get this identity. The expected value of the real minus actual plus the variance of epsilon. So here we call the variance of epsilon the irreducible error, because there's nothing you can really do about it. It's just an artifact of noise from within the system. Whereas this error can be reduced. This is a reducible error because we can get better and better estimates of F. So the mean square error of some function estimate is defined as the average of the squared errors. So this is the actual label in the training data. Here's the predicted label based on the training observation in the data, feature observation in the data. You square those, you sum them up, and then you divide by the number of observations. So if we've got some feature observation x naught with a true label value of y, then the expected mean squared error for that estimate is given by this. And really the punchline here is that you can break this down into two parts. You've got this, which is the reducible error, the bias, and then you've got this. Actually, I think I'm saying that wrong. This is referred to as the bias. This is referred to as the variance. And that just gives a formal treatment of how mean squared error can be decomposed into the variance and bias. But ultimately, the variance bias trade-off, this is kind of some fancy formalism around it. The real idea is that models that have a lot of complexity, meaning that they allow for a lot of flexibility, often have a high bias, and models that have a high bias often don't have very much complexity to them. So said in a different way, the variance of F is the amount it would change if we learned using a different training data. And the bias of F hat is the error that's introduced by modeling something that's complex by something that's much simpler. So learning algorithms that are more flexible have a high variance and a low bias. Algorithms that are less flexible have a low variance and low bias. Another way you can think about it is if you have an algorithm that has a high amount of variance, it's very possible that you're going to get a much different result, a much different prediction mechanism if you put in a new set of training data. And if an algorithm has high bias, on the other hand, it may not work very well in general, but at least it's going to be robust enough that you're going to tend to get a similar prediction mechanism, irrespective of the training data that you put into it. And typically, if you have higher variance, you're going to have lower bias. And if you have a higher bias, you're going to have lower variance. All right, so that's it for notes. These are just some random miscellaneous notes I have. Most of this material came from ISL and ESL chapters 1 and 2. Okay, great. Let us jump in to the next tutorial. Thus far, we've talked about supervised learning problems, where we have features and we're trying to predict labels from features. And if the labels we're predicting are continuous, we call it a regression problem. If the label is discrete, we'll call that a classification problem. In this tutorial, we're going to switch things up a little bit, and we're going to now talk about unsupervised learning. So the goal of unsupervised learning is a bit different. We're no longer trying to predict labels from features. Rather, we are trying to discover interesting or useful things about the features themselves. So this is actually kind of fuzzy. What does it mean to extract interesting things from the data? What is interesting? It's all very subjective, and it's hard to assess if you're doing something successfully or not. So in comparison to supervised learning, unsupervised learning tends to be more ambiguous and more difficult. And it's worth noting that unsupervised learning is often used in exploratory data analysis or as a pre-processing step in a supervised learning problem. You'll do some kind of transformation on your features using unsupervised learning, and then you'll feed those new features that have been processed with unsupervised learning into a supervised learning problem. So in this tutorial, we're going to give an intuitive introduction to principal components analysis, which is simply a technique used to reduce the dimensionality of a set of features. And we're going to apply PCA to our VIX term structure. Let's start by going ahead and importing the package that we're going to need. Import NumPy as MP, import pandas as PD, import Seaborn as SNS, import sklearn, and we're going to also import matplotlib.pyplot as PLT. And I actually don't think we need to do the matplotlib inline. You used to have to do that for the graphs to show up, but that doesn't seem to be the case anymore. Now let's read in our VIX data. df_vix equals pd.read CSV VIX KNN. We can drop our nans. df_vix drop NA. Let's just take a look at df_vix. Okay, great. We also don't need this SPY returns column anymore. So let's drop that. SPY return axis equals 1, in place equals true. And let's look at what we've got. df_vix head. All right, there's our data set. And recall that this data set is the changes on any given day for these various VIX indices. And for this analysis, we're going to want to know the actual levels of VIX on these various days. So that's in a different data set, which we're going to now import. So df_vix ts equals pd.read CSV VIX term structure. I think this also has the SPY returns in it, so we'll drop those. Axis equals 1, in place equals true. And let's look what we've got. And again, this data frame contains the actual levels of these various VIX indices, and this is the day-to-day changes. Before we get into the actual PCA, it'll be useful to do some simple data analysis to get a sense for where df_vix and df_vix ts live in Euclidean space. So these are both of these data sets live in 4-dimensional Euclidean space, but they really live in very certain specific subsets or actual subspaces of Euclidean space. And really it's the goal of PCA to give that observation some more meaning. But before we give the observation some more meaning, let's just actually take a look and see if we can do some data analysis to see what we mean here. So one thing that's true about VIX term structures is that they're usually monotonically increasing. So this means that 30-day VIX is going to be higher than 9-day VIX. 90-day VIX is going to be higher than 30-day VIX, et cetera, et cetera. And let's check what percentage of days this is actually true. So we're going to say condition 1 equals df VIX TS VIX 009 less than or equal to df VIX TS VIX 030. Condition 2, df VIX TS VIX 030 less than or equal to df VIX TS VIX 090. And the third condition is df VIX TS VIX 09 is less than or equal to df VIX TS VIX 180. So those are conditions. Let's make sure that runs. And then we can say df VIX TS condition 1 and condition 2 and condition 3. And how many rows, we're going to check how many rows that's true for and divide it by the total number of rows. And as you can see, on about 70% of days in our data set, there was an upward sloping term structure. So your code challenge, and I'll give you a couple minutes for it, is find the percentage of days in which 9-day VIX is greater than 180-day VIX. And we'll refer to this as an inverted term structure. Okay, let's try this code challenge. So I'm just going to recycle some of this code. And we'll say that condition 1 is equal to when 9-day VIX is greater than 180-day VIX. And I'm going to say, I'm going to reuse this as well. Condition. And there you go. On about 11% of days, we had an inverted term structure. And if we wanted to check that it was truly monotonically decreasing, we would have to throw some conditions in there. But we're just going to, as a shorthand, say that whenever 9-day VIX is greater than 180-day VIX, there's an inverted term structure. So between these two conditions, either monotonically increasing or completely inverted, we're representing about a little over 80% of days. Okay, this is again a code chunk that I don't really want to mess with. So, so that was a description of the shape of the actual term structure of VIX, the actual values of VIX and how they they relate to one another on most days. We can also make similar types of statements on the changes in the VIX term structure, the various points on the VIX term structure, which are saved in df-VIX. And we can see that on about 75% of the days, all the points in the VIX term structure are either going to rise or fall together. So let's take a look at that. So these conditions, this condition is all of the VIX values. Well, let's just, so we know what we're looking at, df-VIX. So this first set of conditions is that all of these are negative. So like this one right here. And this condition is that all of these are positive. So row 5 right here is an example of one. So is row 3. And our big condition is either they're all positive or they're all negative. And I should change this to strictly positive. So there you have it. On about 75% of days, all the points on the term structure either go up or all of them they either all go down. And we can also see this. Another way of saying that is that they're all very correlated with one another, which we can see if we do a pairs plot. SNS pair plot, df-VIX, VIX 009, VIX 030, VIX 090, and VIX 180. And there you go. We've seen this plot before. They're all highly correlated. They all tend to move up and down together. So here summarizes our results. So on about 70% of the days, the term structure is monotonically increasing. On about 10% of the days, VIX term structure is inverted, meaning that 90-day VIX is greater than 180-day VIX. And on about 75% of the days, all the points on the term structure are either going to rise or fall together. So a discussion question for you guys to ponder is, if you were to construct a forecasting model for VIX, would your model assert that all points of the term structure move independently of one another? So it's a little bit of an easy question. The answer is obviously not. Things tend to move up and down together. The VIX term structure has a very particular shape. So you very rarely see, one go up and one go down and, the points moving sort of arbitrarily. So let's talk a little bit about PCA. Again, this is an intuitive introduction to PCA and how to implement it in sklearn. We're not super interested in getting bogged down in the mathematical details, which involves a bit of linear algebra. So here are really the essential ideas of PCA. So let's say we're trying to understand some n-sized set of p-dimensional features. So each of the n feature observations is a vector of p numbers, and we'll want to scale those features so that the components have mean 0 and standard deviation 1. If we do that scaling, we can think of the features as a collection of points living in p-dimensional Euclidean space that are centered around the origin. And it's often the case that there's some Q, some dimension Q that's smaller than P, such that most of the variation of the features can be described by a Q-dimensional linear subspace of RP. And PCA is a technique for finding the basis of this Q-dimensional subspace. And here's actually how you go about computing that subspace. I'm sorry, so PCA is a technique for finding the basis of that Q-dimensional subspace. So you would figure out what the subspace is as well, but really what we're finding is a basis for this Q-dimensional subspace. The first element of this basis is the vector, i.e. some line that goes through the origin, that is collectively closest to all of the feature observations. So conceptually very similar to fitting a regression line. You're fitting a regression line to all these points. And this vector is called the first principal component. And it has a property that if we project our feature observations onto that vector, the sample variance of the projection is maximized. Okay, the second element of this basis is called the second principal component. So what we do is we consider all the vectors which are perpendicular to the first principal component. And among these perpendicular vectors, the second component is the one which best fits the feature observations. And it has a property that if we project our feature observations onto that vector, then we maximize the sample variance of the projections among all those vectors that are perpendicular to the first principal component. And we repeat this process Q times until we get our Q principal components. Let's see how this actually looks in sklearn if we use our df-vix data set. We're going to start by normalizing our features so they have mean 0 and standard deviation 1. From sklearn, pre-processing, import scale. We're going to do our feature selection. So x equals df vix, vix 009, vix 030, vix 090, vix 180. And we're going to scale our features. So xs equals scale x. And as per usual, we will bring in our constructor function, then we'll instantiate our model, and then we'll fit it, as we do all the time with sklearn. From sklearn, decomposition, import PCA. PCA equals PCA with n components equals to 3. And PCA fit our scaled features. We can view the actual principal components with this components property. PCA, print PCA components underscore. Those are our principal components right here. They're all orthogonal to one another. And we can see the overall variation that's explained by each of these components by this explained variance ratio. Print PCA explained variance ratio. So about 95% of the total variance is explained by the first component, 4% for the second component, and right around 1% for the third component. And here's your code challenge that I'll give you guys a few minutes to do. Try refitting the PCA with 4 components and check, are the first 3 components the same as before? What is the total amount of variance explained by the 4 components? See if you can guess what that is before you check. And what happens when you set the number of components equals to 5 and try to refit. Let's go ahead and try this. So this code is the same as before. We just want to do 4 components. And then if we check, so let's do that. It ran. If we print our components, yes, the first 3 are the same as before. It's really a deterministic process. And finally, oh, let's do this. You can do PCA variance ratio explained. I believe that's a list, so we can just sum it. Right. 100% of the variance is explained by these 4 components. And if we try to run this all for 5, it gets mad at us because we're starting with a 4-dimensional space. So there wouldn't be 5 principal components. So let's get an intuitive understanding of these principal components. So these terms come up frequently: level, slope, and curvature. People talk about them in the context of yield curves because you can do a very similar analysis to show that most of the time interest rates all move up and down together. But there's also some secondary effects where the slope of the yield curve changes and the curvature changes. But let's get a sense for what that means. So the first component represents parallel shifts in the VIX term structure. All the points are either increasing or decreasing. So you can see this first principal component, they're all positive and they all have a similar sort of magnitude. So if you multiplied a scalar by this, all the numbers would sort of rise and fall at a similar magnitude. So again, 95% of the total variance explained by these parallel shifts of equal amounts. Another way of saying that is that all the points in the term structure are very strongly correlated, positively correlated. Although this makes an even stronger statement that when they move, they tend to move by the same amount, in fact, not just move in the same direction together. And we can also see that we saw above that 75% of the days, all the points either moved up or moved down together. So the second component represents the front of the curve going up and the back of the curve going down, or vice versa. As you can see, you've got a positive number and a smaller positive number, then a negative number, and then an even more negative number. And so this represents the front of the curve going up a lot, the middle of the curve going up a little bit, the back of the curve going down a little bit, and then the very back of it going down quite a bit. So these are changes in the slope of the term structure. And these changes in slope represent about 4% of the total variance. And if you recall, on about 70% of days, there was a purely upward sloping term structure. And on around 10% of the days, there was a downward sloping term structure. The 9-day VIX was actually higher than the 180-day VIX. And in order for the term structure to have that kind of change, you would have to have a very significant change in slope. In fact, it would go from positive to negative. But oftentimes you see just a flattening or steepening of a upward sloping term structure too, which is a similar type of transformation. An inversion is an extreme example of a change in slope. And lastly, we have changes in curvature. So this third component is the two ends decreasing while the middle of the curve increasing. And so what that represents is the curve going from more convex to more concave and vice versa. All right, so that rounds out the PCA tutorial. Let's talk a little bit more about linear regression in particular. And we're going to focus on simple linear regression. I have some notes on multiple linear regression. We might get to those later in the course, but we'll just focus on the simple linear regression. The multiple linear regression is really just kind of a generalization of some of these concepts. So here's the essential setup. In simple linear regression, we're trying to predict a quantitative label, y, from a single feature x. And we assume that there's a linear relationship. So y is approximately equal to some constant plus some constant beta 0 plus beta 1 times x. And we start with some training observations and we seek to estimate this beta naught and beta 1. And we denote those beta hat naught and beta 1. In order to do these estimates, we define the residual sum of squares as follows. It's simply the actual label minus the predicted label. You square it up and you sum up all those residual sum of squares. You sum up all those squared residuals. And we really want to choose beta naught and beta 1 such that this residual sum of squares is minimized. And as you well know, the geometric intuition is that we're fitting the best line to our training data. And if you actually do this minimalization problem, you end up with these expressions for the beta 1 and beta naught parameters. So these estimated regression coefficients are simply functions of our training data. And that is to say that they are statistics of our data, which leads us naturally to calculating confidence intervals and hypothesis testing, which is the purview of more standard statistics. So under the statistical view, we think of our training data as resulting from random sampling, and therefore our beta naught hat and beta 1 hat are statistics. And we may want to calculate the variance of the sampling distribution of these statistics so that we can form confidence intervals around these beta knots to determine things like significance. So these variances are referred to as standard errors, and they're defined as follows. So this is the variance of the distribution of beta hat naught, and this is the variance of the distribution of beta hat 1. And these beta hat naught and beta hat 1, they are random variables in the sense that they are simply functions of random outcomes of a random variable. So what is this hypothesis testing that people always talk about? The starting point of our linear regression is an assumed linear relationship between our label X and our feature Y. And if the true beta 1 is equal to 0, then this would mean that there's really no relationship with the feature and the label at all. The magnitude of our coefficient estimate represents the strength that we estimate this relationship to have. If it's really big, then it's a really strong relationship. If it's small, there isn't much of a relationship at all. So hypothesis testing refers to assuming that the true beta hat is 0, an assumption which is called the null hypothesis, and then calculating how unlikely it is that we'd observe the beta hat 1 if this were the case. So one of the cruxes of this argument is that these standard error estimates really don't depend on whether beta hat naught and beta hat 1 are 0 or not. So the standard error estimates remain valid, irrespective of whether the null hypothesis is true or not. So what we do is we calculate the t-statistic, which essentially represents the number of standard deviations away from the mean our coefficient estimate is. And assuming this null hypothesis is true, then the t-statistic has this value. And you can show that under certain assumptions, the null hypothesis, that if the null hypothesis is true, then this t-statistic has the t-distribution with n-2 degrees of freedom. But it's better to think that if you have any kind of reasonable sample size of n greater than 30, that this thing is essentially normally distributed. So a large t-statistic simply means that the size of the beta coefficient is much, much bigger than the standard error. And so we could have confidence that beta 1 is not equal to 0. And in statistical jargon, they say that this means that we would reject the null hypothesis. So under the null hypothesis, the t-statistic is approximately normally distributed. And the p-value of the t-statistic is the probability of seeing a t-statistic of larger magnitude, which could be calculated by looking at the normal distribution. So a small p-value means that a larger t-statistics would be very, very unlikely, which again gives us confidence that beta naught is equal to 0. And as a matter of convention, I don't know, I forget where this actually started, but people started assigning a p-value of 0.5 special meaning. So basically, if you had a result that had a p-value of 0.5 or less, it would seem like a good result. But if it was lower than 0.5, it would mean it was a bad result. So let's talk about the residual standard error. So again, we're assuming this simple linear relationship between y and x. And then the residual standard error is an estimate of the standard deviation of epsilon and is given by this. So you take the RSS, you divide it by n minus 2, and you take the square root. So the residual standard error is a goodness of fit measure, but it's kind of hard to interpret because it's expressed in units of y. And so we prefer to use something called the R squared, which gives us a unit-free measure of goodness of fit. And R squared is, of course, what's produced by the score function in the linear regression model in scikit-learn. So probably the easiest way to express R squared is in terms of residual sum of squares and total sum of squares. So we have R squared is just total sum of squares minus residual sum of squares divided by total sum of squares. And TSS and RSS are defined this way. So the value of R squared is always between 0 and 1, and it can be interpreted as the percentage of the label's variance that's explained by the feature. And this is actually a useful shorthand that it took me a long time to learn, but in this simple linear regression setting, R squared is just equal to the correlation squared of the two variables. The correlation of the two variables squared, rather. Okay, I think the rest of this is multiple linear regression. And what do we have next, I think? It's the student loan stuff, which I don't want to crack into at this point. So I think we will just call it a day, and I will stick around for questions if you have them.